Welcome to my first video on a new series I'm starting called OrCad Projects. I'm pausing at this screenshot because this is my weird attempt to try and hack a thumbnail into my YouTube video. But I guess the purpose of this series is to develop projects from the beginning to end within OrCad. So that includes coming up with the circuit I want to, designing the schematic in OrCad, laying out the PCB in OrCad PCB Editor, and then actually getting the thing manufactured and demonstrating it for you guys. So with that, I guess I'm going to start the video. To do all these projects, I'm going to be using OrCad. So if you don't have it, let me adjust my screen here. I think that'll be good enough. To do that, you need to download OrCad Lite. So just Google OrCad Lite and this free OrCad Lite download. This is the page and the download link for it. They do make you fill out kind of like a survey in order to download the software, but it's kind of a pain in the neck, but it is good software and a lot of professional companies use this. So if you're ever looking at using this for a job, or even it's just pretty good software for a hobbyist. So this is what I'll be using. Here is kind of what it looks like. Here's OrCad Capture. This is what you use to design your schematics and simulate your circuits as you go along. And here's OrCad PCB Editor, and this is what you use to design your PCBs and actually get something manufactured. So let me think. This first video is just the introduction. So all I'm going to be going into is the circuit I'm going to be trying to design and the basic concepts of how it's going to work, and then in the next videos we'll go into each step of that. So let's see. Oh, sorry about that. Let me get this in the right spot. Oh, come on. Okay. So I just drew up a bunch of PNGs that I'm going to use to explain what I'm going to try and do. Here is the final project circuit, and it's really just a boosted flashlight is what I'm going to call it. And all it is I'm taking in voltage from two AA's, so my VN is going to be around 3 volts. And then I'm using a boost converter to step that up to about 30 volts to power a bunch of LEDs. And why would we want to do that? Well, really it's just I wanted a project that would be simple enough to design but also interesting to design, and I've always wanted to mess around with the boost converter, so I figured I'd take the opportunity. And another reason is they actually use boost converters in hybrid electric vehicles a lot, and then also in lighting. And I think I might have an example of when you might want to use it in lighting. So here's a basic LED circuit. You've got like some voltage source, in this case it's 3 volts, going to an LED, and then you have your current limiting resistor down here. If you don't know what this is for, if you're really just starting out, basically an LED can only handle a certain amount of current through it. In order to know what that current is, you have to read through the data sheet, but in general it's usually around 15 milliamps or something like that. So depending on what your input voltage is, an LED has a certain voltage drop across it when it makes light, and so that's going to leave you with some extra voltage down here potentially that, well, okay, if you don't put a current limiting resistor down here, the battery is going to supply however much current this LED wants, and sometimes that's going to be more than the 15 milliamps that is a good rating for it. So your LED will break maybe instantly, or maybe over time it'll be damaging to it. So you put this current limiting resistor in here to whatever voltage is left over after the forward voltage of the LED. You're going to do your current equals V divided by R to set the current through this series loop. And hopefully I can make that clear if that didn't make any sense later on. But So here's the first example where your LED has a forward voltage of 1.8 volts. And what that means is in order for this LED to turn on, it needs 1.8 volts across it. So in this case, I have 3 volts coming in. So that's greater than this 1.8. So I'm left with, well, 1.2 volts left over down here. And so if I wanted to limit this to a certain current value, I adjust this resistor to do that V, or I equals V divided by R, to set whatever current I want through this series connection. And so in this case, since Vn is greater than Vf, my LED is going to turn on. But if I had a case where maybe my forward voltage was greater than the input voltage, so I have 3 volts coming in, but this LED has a forward voltage of 3.4 volts. So since I don't give it enough to begin with, it's never going to turn on. So sad face, sad day. And actually a lot of the white light lighting LEDs, they do have higher forward voltages. And one thing you'll notice if you look through a bunch of LED data sheets is the forward voltage depends on a few things, but really there's a clear correlation between forward voltage and color. So red LEDs usually have the smallest forward voltage, and then you go across the spectrum up to blue to get your higher forward voltages. And of course white light's most similar to blue. As you go up, well, white light's a combination of everything, but that's kind of the way that spectrum goes, is red's the lowest forward voltage up to blue. And so in this case, since my input's not great, isn't large enough to turn on the LED, nothing happens. So where the boost converter comes in is what it does. The function of a boost converter is to take an input voltage and then boost it or increase it to a higher voltage. So in this simple circuit, I have a 3 volt input. It goes through a boost converter, and the boost converter outputs 5 volts. So whereas before, where I had this forward voltage of 3.4 volts, so this LED wouldn't turn on, now with the boost converter I have 5 volts across it, and so I can power that thing even though my input's still only 3 volts, which is pretty cool, and it's a pretty cool circuit to build. So I kind of need to explain how this boost converter works. That's going to be the fun part of this design, and I've decided in this series, for each video, I'm going to try and come up with a lame metaphor to explain how the focus of the project works. So in this case, I am equating the boost circuit to this situation here. So let's say I have a dad and his daughter, and the dad wants to lift his daughter up. Maybe they went to the park and they're having a really fun day, and he wants to pick up his daughter like in celebration. So it's easy for the dad to do that, and he could lift his daughter up to 5 feet in the air, no problem, because he's a lot bigger than her and he's stronger than her, and she's a light load for him to pick up, and so he can lift her to 5 feet really easy. But what if the daughter wanted to lift the dad to 5 feet? I know that's kind of ridiculous, but what if she wanted to? Well, she's probably not strong enough to do it, so the obvious answer to that is to make her jacked. But even then, she's still not tall enough to get him up to 5 feet, so that's going to be an issue. And so the correlation between that and the previous circuits is, in this case, the dad's strong. He's strong enough to lift the daughter easily. She only weighs 1.8 volts. He can apply 3 volts, so it's no problem. But when the daughter tries to lift up the dad weighs 3.4 volts, and the daughter can only lift 3 volts, and it just doesn't work. So even as strong as the daughter is, she can't do it. So how could someone who can't lift up someone else pick them up to 5 feet in the air, get them up to 5 feet in the air? That's what we need to do. Well, how we're going to manage it in this metaphor is with a swing. And I really like the idea of a swing for a boost circuit, and I'll explain why. And I think the metaphor actually holds up pretty well, but not perfectly. But basically, here's how it's going to work. Even though the daughter's not strong enough to lift the dad just straight up 5 feet in the air, she is strong enough to give to give him a small push on a swing. So, you know, she reaches up and she pushes him, and if she does that again and again, each time she applies whatever strength she can. She gives him a good amount of force, and he moves a little bit, and then the next time maybe he moves a little bit more, and the next time more and more and more, until finally she gets him up to 5 feet. So even though she's not strong enough to do it all by herself, if she has a swing, she can get her dad up to 5 feet in the air just with the small impulses that she's able to provide. So that's what the boost circuit does in a similar fashion. And I'm going to break down kind of how these things go together between circuit elements and what I just said, my silly metaphor. But basically, here's the end circuit we're going to be designing. And I have my input of 3 volts from 2 AA batteries. I wanted to power this flashlight off 2 AA batteries. And then I wanted to string together 8 of these LEDs with a 3.4 forward voltage drop, and string them all up in series. That way, well, I wanted to see like a large output voltage. I thought it'd be cool to boost 3 volts to something large. So in this case, I said let's do 8 LEDs. 8 LEDs times their forward voltage should give me the minimum V out I need here. So the minimum voltage I need to apply to them to give me to let them turn on. So if I take my 8 LEDs times the 3.4 forward voltage, then I need a minimum of 27.2 volts on my output of the boost converter. In other words, I need to apply at least 27.2 volts to my load, which is all my LEDs and the current limiting resistor, in order to get them to turn on. So I figured, what the heck, I'll go to 30. So input of 3, output of 30 on the boost converter. And the metaphor, if you remember, it holds up. We have our daughter, and she's our input battery. She's not strong enough to turn on all these LEDs in series. Definitely not. So, but she's a battery, and her dad is our load, which is all those LEDs with the current limiting resistor. And the boost circuit here is the swing set. And I think I was going to go into a little bit of theory on this, but I think I'm going to do that in each individual video. So I'm going to stop this video shortly, but those are the basic building blocks to this design. And again, this boost circuit's similar to a swing in that we're gonna, even though we can only apply 3 volts, we're gonna do it with impulses, and as long as we get our timing right, just like the little girl pushing on the swing, she has to push at the right time in order for the swing to go higher and higher. If the dad's coming backwards and she tries to push forwards, she's gonna get obliterated, and it's gonna be a horrible day at the park for both of them. But if she waits every time for him to get within range of her arms, and she pushes him when he's in that correct window of time, then he'll go higher each time, and higher, and she'll be able to lift something that she couldn't have before with the help of the swing. And that's the exact same thing we're going to do with this boost circuit. And I've actually finished the project, so here's what it's going to end up looking like in the end. It's a pretty cool design. The thing's super bright. I think it's like 200 lumens. And even the camera doesn't do it justice. I can't look at that thing without seeing dots for like the next half hour. So that's going to be the project. If you're interested, feel free to follow along. Hopefully I'll get these videos uploaded in a pretty timely manner. But again, I'm going to go through each step, showing you the next few videos are going to be on the theory of how the boost circuit works, just simple layman's terms. And I'll show you the links to the Wikipedia articles to help you make more sense and to derive the mathematics. But I'm just going to talk about, you know, how it works practically, and then go into designing the circuit in OrCAD and showing you simulations of it working in OrCAD. And then after that, once I have the schematics finished, I'm going to show you how to select components on Mauser or DigiKey in order to, probably Mauser, that's the one I'm more familiar with, in order to make sure your circuit's going to work and nothing's going to break, and to get the footprints to put on your PCB. And the footprints is basically the component outline that you're going to drop down on your board, and how to connect all those up. And then I'll go into creating the printed circuit board files in OrCad PCB Editor, and then I'll show you even how to upload the Gerber files to a board manufacturer if you want to do that and create your own circuit. So that's going to be what this series is, and that's going to be what this first project is. So thanks for watching. Catch you later.